We have discovered the star with the lowest amount of iron of any known star. It's located in the constellation of Scorpius, and it's actually on the other side of the Milky Way. So it's just beneath galactic center, but on the other side from the Sun.
So this discovery is really exciting because it tells us something about how the universe was shortly after the Big Bang. So the first stars would have formed maybe after 100 million years, 200 million years after the Big Bang, and they really transformed the whole universe. The first stars that were formed were predominantly very massive, so they would have died by now. So they only lived for a few million years, so none of them would have survived to the present day. So we can't actually discover these stars. What we can do is discover the next generation of stars, because they will contain the traces of the first generation of the stars. So this star that we have found now is one of these second generations of stars.
All the heavy elements found in stars were created in supernovae. So at the beginning of the universe, only hydrogen and helium and some lithium was created. Everything else came from generations of supernovae. This star has a very low concentration of all these heavier elements, which means that it has a very small contribution from supernovae. So it must have been born very early in the evolution of the universe. So this particular supernova was actually very weak. It was weak enough that the heavy elements that formed near the core of the star that exploded didn't get enough energy to escape the gravitational well. So instead they fell back into the neutron star that formed at the core of that massive star that was exploding. And because they fell back in, that's why this star that we've discovered is so poor in iron and other heavy elements. So essentially the only element that could escape was carbon, and everything else was trapped, fell back into the star.
Stars have what we call an onion shape, where we have heavy elements like iron in the beginning and lighter elements like carbon in the end and the outside. And our early type stars might not explode in supernova like we think stars do, and so it could just be we're not getting the heavy element enrichment such as iron, and so we're only getting the carbon that can form in the early stars.
So we use data from the SkyMapper telescope that has mapped the entire southern sky painstakingly using photometry, so measuring the average color of a star. Using this, we identified roughly 20,000 candidates that appeared to be very metal poor, and we have been following these up one by one with a spectrometer on the ANU 2.3 meter telescope.
We are going to continue observing in a little bit more detail to really understand what the chemical makeup of the star is, because that's going to tell us more about what kind of supernova preceded it.
So it's going to be really exciting to see, how our observations of these isolated, low abundant stars shape our models of star formation as we move forward.